I'll get started. So, worksheet 16 through 18 are due on the 16th. That's next week. On Thursday, homework number 2, also due on the 16th, next week on Thursday. And exam number 2 on chapters 16 and 18 will be on the 16th. It'll be 60 questions like the previous exam. Additionally, the semester project topic is due on the 21st. And make sure you sign in on the sign-in sheet. And so, regarding the semester topic, there's a list of suggestions up on Blackboard. You can pick any of those, but you don't have to pick any of those. You can make up your own topic. So, igneous rocks. We're talking about rocks. Igneous rocks are rocks formed by fire. They form from molten rock. So they form as magma cools and crystallizes. If they form inside the earth, they're called plutonic or intrusive rocks. And if they form on the surface, they form from lava, which is just magma that has left the inside of the earth. But in that process, it loses its gas. And these are called volcanic or extrusive rocks because they come out of a volcano. In general, they're composed, igneous rock tend to be composed of ions of silicate minerals. The ions are arranged in orderly patterns during cooling, and the size of the crystals is determined by, note yourself, do not look into the projector. By the rate of cooling. So if you cool down slowly over a long period of time, you can build large crystals. But if you cool down very fast, all the crystals that form are very small. So a slow rate will form large crystals, a fast rate forms microscopic crystals, and a very, very fast rate will form a glass. No crystals will have a chance to form at all. They cool down so fast that it basically just sort of locks the disordered liquid state in place. These are mainly composed of silicate minerals. There come in 2 types, the granitic or felsic compositions, which are richer in light silicates. They're called granitic because the most common example is granite. But the general term, more technical term is felsic, and then the basaltic or mafic compositions, which are richer in dark silicates. Again, named after the most common type is basalt. But they're also called mafic. So the igneous rocks can be split, by their composition. They can be granitic or felsic, andesitic or intermediate, basaltic or mafic or ultramafic, or they can be coarse-grained or fine-grained. Coarse-grained granitic is granite, fine-grained granitic or fine-grained felsic is rhyolite. Coarse-grained andesitic is diorite, fine-grained is andesite. Coarse-grained basaltic is gabbro, fine-grained is basalt. So granite is coarse-grained, basalt is fine-grained. And then for the ultramafic, coarse-grained ultramafic is periodite. In theory, fine-grained is comatite, and ultramafic rocks are very, very rarely extrusive. So you do not usually see that. And you get more light-colored minerals in the granitics and more dark-colored minerals in the basaltics and mafic, the mafics. And in general, you get increasing silica as you go this way, go towards the granitic. You get increasing potassium and sodium as you go towards the granitic. And then as you go towards the mafic, you get, so felsics have more silica, more potassium and sodium. Mafics have more iron, magnesium, and calcium, and the temperature where melting begins is a higher temperature. So here is a short video about igneous compositions.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe how to determine the composition of an igneous rock. So take a look at these 4 samples of igneous rock. They all have the same texture, which means they all have the same grain size. The crystals are about the same size. They're easily visible to the naked eye. However, it's readily apparent that they have different colors. And those different colors are reflective of the different minerals that make up these igneous rocks. So this rock right here is dominated by ferromagnesian minerals. This rock right here is dominated by minerals that are rich in silica. And this rock here and this rock here are somewhere in between in terms of their composition. Now there's a diagram in your textbook that describes the relationship of igneous compositions to one another between different igneous rocks. It looks something like this. What we want to focus on here at first is the center portion of the diagram, these strange looking shapes that are different colors. I want to add some labels in here that show that these are the proportions of different minerals. So over here on the far left you can see percent by volume, and there are some igneous rocks that basically their entire volume consists 100% of olivine. They're totally dominated by olivine. There are other igneous rocks that have, say, 40% olivine and about 40% pyroxene, maybe a smidge of amphibole, and then the rest is plagioclase feldspar. So that's the way to read this diagram, is sort of make these slices that go through it from bottom to top and calculate basically how much percentage of the different minerals are there. Let's go over all the way to the left side, and you can see that there are some igneous rocks that have some amphibole, some biotite, a fairly sizable chunk of the sodium-rich variety of plagioclase feldspar. Then they've got potassium feldspar, quartz, and muscovite. Notice that you're never really going to find an igneous rock that has muscovite and, say, pyroxene, because there's no vertical slice that you can draw through this diagram that intersects both the pyroxene shape and the muscovite shape. So there are certain minerals that occur together and other minerals that occur together. Let's go ahead now and take a look at the bottom part of the diagram. So let's bring these arrows into relief and add some labels. You can see here that these arrows at the bottom show dominant trends. There's more silica on the left side of the diagram, and there's more potassium and sodium over there too. On the other hand, there's more iron, more magnesium, and more calcium towards the right side of the diagram. And then very importantly, in terms of partial melting, the temperature at which melting begins is very different from the left side to the right side. The left side will begin melting at as low a temperature as 650 degrees Celsius, while the right side you really have to get it quite hot, up to 1250 Celsius. The last part of the diagram that we haven't looked at yet is up at the top, and this basically takes all this complication and simplifies it. We divide igneous compositions up into 4 major categories, and those 4 major categories are felsic, intermediate, mafic, and ultramafic. When your professor or your lab instructor asks you what composition an igneous rock is, they're asking you for one of these 4 choices. Is it felsic, intermediate, mafic, or ultramafic? You can get there by basically identifying the different minerals that are present, and then those minerals will lead you to a certain composition. The other thing that you'll be paying attention to in lab is the texture. And here we've got 2 textures listed, coarse and fine-grained. Okay, let's go ahead and test you now at this point. Here's an igneous rock. Identify what its composition is. Okay, so hopefully you were able to identify a few of those minerals pretty easily. Quartz is pretty easy to pick out. It's sort of gray and glassy. It breaks with a conchoidal fracture. The other one that's really easy to pick out here would be potassium feldspar, which is pinkish in color. Plagioclase feldspar is a little bit tougher, but it's whitish in color, and it's got two nice, well-defined planes of cleavage. And then there's also some dark minerals in here, and these are amphiboles. So if you look at all of those minerals relative to one another, you'll see amphibole and plagioclase feldspar, potassium feldspar, and quartz. All of those minerals are minerals that are most common in felsic igneous rock. So we would have to say this is some kind of felsic igneous rock. And then to choose between rhyolite and granite, we'd have to look at the texture. Thank you very much for your attention. This has been another Smart Figure.
So, the texture is the size, shape, and arrangement of the minerals that make up the rock. So you can have a fine grained texture where everything is very small. A coarse grained texture. So a fine grained texture happens when you have a fast rate of cooling. A coarse grained texture happens when you have a slow rate of cooling. A porphyritic texture is one where you have two different crystal sizes. This is when there were two rates of cooling. Glassy is a situation where there's a very fast rate of cooling. And vesicular means it contains holes that are left behind by gas bubbles. So it's like pumice, it's full of little holes. And pyroclastic is fragmented. This is produced by the consolidation of fragments from volcanoes. Because volcanoes will spit out rocks that break into pieces or shatter, and then they can all glom together. So here's some examples. A glassy texture you have composed of unordered atoms that resembles dark manufactured glass. Porphyritic texture is composed of two distinct different crystal sizes. This happens when you have two different rates of cooling. Coarse grained is where the mineral grains that are large enough to be identified without a microscope. You have a fine grained texture where the crystal's too small for the individual minerals to be identified without a microscope, like magnifying. Pyroclastic is a fragmental texture. You can see this is sort of glued together, sharp, pointy fragments, or the ash, once molten blobs, angular blocks that were all ejected during an explosive volcanic eruption. And then a vesicular texture is extrusive rock that contains voids left behind by gas bubbles that escape as the gas solidifies. Sorry, as the lava solidifies, the gas is escaping in bubbles, and you get this pattern. It's basically foamy. So those are the different sorts of textures. They come from different sorts of productions. A lot of them come from volcanic locations.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the major kinds of igneous textures, and you should say what they mean about the history of the igneous rocks in question. So take a look at these four samples of igneous rock. You'll notice that they have some differences, but they also have some similarities. The difference that probably jumps out at your eye immediately is that they are different colors. Those different colors are reflective of the different minerals that are present in these different rocks. But what they have in common is that all four samples here have about the same size of crystals making up the rock. They all have the same texture. There are a bunch of different kinds of igneous textures, some of which form below ground in intrusive igneous environments, and others that are distinctly volcanic that are produced in extrusive igneous environments. Let's examine a few of them. There's glassy, porphyritic, phaneritic, vesicular, pyroclastic, and aphanitic. The basic breakdown is the difference between aphanitic and phaneritic. Aphanitic textures are very fine-grained, meaning that you can't see the individual mineral crystals with the naked eye. You need some sort of microscope. Whereas phaneritic igneous textures are typical of intrusive igneous rocks. They have very big crystals that are readily visible to the naked eye. So aphanitic basically means small crystals, and that's typical of volcanic rocks, and phaneritic means big crystals, typical of plutonic rocks. Other volcanic textures include vesicular, which basically has little tiny gas bubbles These gas bubbles formed when the lava decompressed upon eruption, and it produced bubbles just like when you open a can of soda. That soda degasses carbon dioxide. But in this case, the lava set up and solidified around those bubbles before they had a chance to pop. Another distinctly volcanic texture is the glassy texture. This is what happens when you have a very dry lava or when you have a lava that is cooled very, very rapidly. It ends up not having the ability to form mineral crystals, and so you get glass instead. Two other volcanic textures are here, a frothy volcanic texture and a pyroclastic texture. The frothy volcanic texture is basically lots of little vesicles. It's typical of the rock called pumice. The pyroclastic volcanic texture has chunks of other rocks in it, and these chunks of other rocks are basically the signature of a violent volcanic eruption. So it's been broken by fire, or pyroclastic. There are also textures that are indicative of intrusive conditions. So a porphyritic texture is characterized by two distinct crystal size classes, very big phenocrysts, which are set in a very fine-grained ground mass. And that's what happens when you have two stages of cooling. One slow underground, and then that's followed by a more rapid phase of cooling. You can also have a pegmatitic texture. Pegmatites have very, very large crystals. You can see here, compared to a quarter for scale, that the crystals are greater than 2 centimeters across. And so that's an indication that this igneous rock formed from a very, very wet magma. The water in the magma helped ferry around the different elements so that really, really large crystals could grow. So let's go ahead and test you here. We've got this diagram from the textbook. Let's go ahead and throw the pegmatite in there as well. Tell me, which environment, extrusive or intrusive, has the greater number of textures that are possible? Hopefully you said that extrusive is the more diverse textural realm. As we see, there are a whole bunch of textures here that can form in extrusive or volcanic environments. In the diagram, we actually only have one intrusive texture, the phaneritic texture, recorded, and then we added in the pegmatite as well. But aphanitic, pyroclastic, frothy, glassy, and porphyritic are all typical of extrusive environments. This has been another Smart Figure. Thank you very much for your attention.
So the main thing that determines texture is your cooling rate. So if a magma cools very slowly deep within the earth, you get these large crystals like you see in granite. If it cools very rapidly at the surface, you don't have sufficient time to form these crystals. So you get smaller crystals. And if it cools extremely rapidly, no crystals form, you get volcanic glass. So this is basalt, which makes smaller crystals. It's got disorganized line. So here are some extrusive igneous rocks. You can see they have very fine crystals, while an intrusive one has larger crystals. So granitic rocks, felsic rocks are composed of light colored silicates. They have lots of quartz and feldspar. Some common ones are granite, rhyolite, or obsidian. And andesitic or intermediate rocks, they're a mixture of felsic and mafic compositions. Andesite and diorite. Basaltic rocks are mafic. They're composed of dark colored silicates. The common ones are basalt and gabbro. There are also ultramafic as well. So here's sort of all the different textures and all the compositions. You very rarely see anything other than peridite for ultramafic. You see the basaltic and the granitic and the andesitic. And there's, coarse grained, fine grained, those are the common groups. And then there's the porphyry, the porphyritic ones, the glassy ones, the vesicular ones, and the pyroclastic ones. So this is how you can classify them as well into various groups based on their texture and their composition.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to use the characteristics of an igneous rock, its composition and its texture, in order to classify it by name. There's a lot of different kinds of igneous rocks. As you look at the suite of samples here on the screen, I hope you'll notice that some of them are darker in color, some are lighter in color, some have big, obvious grains, others have very small grains that you can't see. There's a lot of variety here. So how can we make sense of all that variety? It turns out there's a really nice chart in your textbook that explains the difference between the different igneous rocks. This chart is organized according to mineral composition on the horizontal axis and texture on the vertical axis. So basically what this boils down to is if you know the composition and the texture of your igneous rock, you can give it a name. Composition refers to what minerals are present in the igneous rock. The proportions of the different minerals vary, but you're unlikely ever to find olivine, for instance, in the same igneous rock as quartz. Quartz is associated with one set of minerals, and olivine is associated with another set of minerals. And then, of course, there's some possibilities in between, where you have other compositions. There are also accessory minerals. So these are minerals that are present in relatively small amounts. And then there's this sort of handy rock color classification scheme, which is based on the proportion of dark minerals that are present in that rock. In general, though, what this boils down to is that we can classify igneous rock compositions in one of four categories. They're felsic, intermediate, mafic, or ultramafic. When it comes to texture, we've got a bunch of possibilities as well. So, what happens when we put these all together? Well, it looks something like this chart in your textbook. Let's go ahead and build the chart out piece by piece. Let's say we've got an igneous rock that has a felsic composition. So we see minerals like potassium feldspar and quartz in there, definitely felsic. And we can tell that those grains are actually big enough to see with the naked eye. So we would say it's coarse-grained or phaneritic. That rock is called a granite. Granite has a very specific meaning when it comes to igneous rocks, and it means specifically a rock that is both felsic and phaneritic. On the other hand, let's say we have a mafic composition instead. It's still coarse-grained. That's not going to be a granite. That's a different rock name because it has a different composition. That one's called a gabbro. Similarly, we've got a diorite, and a diorite has an intermediate composition and a coarse-grained texture, or you could have a peridotite, which is ultramafic and has a coarse-grained texture. What about if we have that same felsic composition as the granite, but instead of being coarse-grained like a granite, it's fine-grained or aphanitic? That would be a rhyolite. So rhyolites and granites are essentially the same composition of rock, but one was magma and one was lava. Similarly, the fine-grained version of diorite would be an andesite. If you took the magma that would have cooled into a gabbro and erupted it out of a volcano, you get a basalt. There's another kind of rock called a komatiite, which is not very common, which is basically an ultramafic volcanic rock, but for most purposes, you're not going to need to know what a komatiite is. Let's consider the next textural row here, which is a porphyritic texture. Remember, that means two distinct grain sizes. Say we have an intermediate composition, that would be an andesite porphyry. Similarly, a granitic composition could give us a granite porphyry, or a basaltic composition might give us a basalt porphyry. There's no real good examples of ultramafic porphyritic rocks, so ultramafic in composition and porphyritic in texture. So we're going to just go ahead and put uncommon there. And in fact, let's just go ahead and continue uncommon all the way down to the bottom of the chart. We don't really need to pay any more attention to the ultramafic rocks in this chart. You could have a glassy texture. This gives you obsidian. The most common way to get obsidian is with a felsic lava. However, you could also sometimes get it with andesitic or mafic lavas, but they're not as common. The next textural classification is a vesicular texture, such as we find in pumice or in scoria. Pumice tends to be more felsic, scoria tends to be more mafic. And lastly, we have the pyroclastic or fragmental textures. Tuff and volcanic breccia are the rock names here. Tuff is basically made out of very small fragments only, whereas volcanic breccia is made out of small and big fragments. Thank you for your attention. This has been another Smart Figure.
So, to understand why we get these different types, we can look at what's called Bowen's reaction series, which is about the order in which various minerals crystallize out. And this leads to different magma temperatures crystallizing out different minerals and thus forming different rocks. So this is basically the process by which you'll get the higher temperature minerals will crystallize first and settle out. Then you'll get lower temperature ones and so on. And so this is called partial melting, and you get different compositions because of it. So the sequence in which minerals crystallize from magma at high temperatures, you get ultramafic things. So things like olivine will crystallize out. Calcium rich pelagic feldspar. Then the mafic ones, where you have pyroxene and amphibole. The intermediate ones, we have amphibole, biotite mica, and the calcium rich pelagic feldspar. And at the lowest temperatures, you have the felsic ones, where you have potassium feldspar, muscovite mica, and quartz are all in there. So higher temperatures, so hotter magma leads to more mafic rocks. Cooler magma tends to lead to more felsic rocks. And things get divided based on sort of partial melting. So if the rock, so the other thing is that if these minerals will melt out first, but as you have very hot magma that cools, you'll first form mafic rock or mafic material, and then you'll later form felsic material. Now, so that was igneous rocks. Now we can move on to sedimentary rocks. So sedimentary rocks are rocks that are made of basically bits of previously existing rocks. This can either, in general, they form from sediment, pieces of rock that have weathered off of existing rocks and have been carried somewhere else. Various processes will weather rocks. We'll get into this in more detail later, but you could have weathering. The most common one around here is probably frost wedging, where if you have any sort of small crack, water will enter the crack, freeze, expand, widen the crack. Then it will melt, flow into the bottom of the crack, freeze again, repeat. This process will repeat and eventually break apart rocks. It's also why we have so many potholes. Same process works on the streets. So other processes can happen in other places. You can have that's a physical weathering, just a breaking into pieces. There's also chemical weathering, where basically slightly acidic rainwater can dissolve certain minerals out of rocks and things and change them. So exposure to rainwater could cause, say, feldspars to turn into clays. So about 75% of all rock outcrops on the continent are sedimentary rocks, but it's just the surface. So most of the crust is igneous rock. All the sedimentary rocks are sort of a layer on the surface. But because they form from sediment, they're extremely useful for figuring out history, because they form from piled up material that piles up over time. They preserve, each layer is from a different point in history. So you can look back and identify things that happened in the past. So they give you clues to past environments. They provide information about the transport of sediment, how stuff moved around, because you can see, well, this sediment, where the sediment that made up the rock came from. You can try and figure that out. And rock, this is where you get fossils, which are some of the most useful and interesting things you can get in rocks. Like fossils preserve bits of animals, plants, etc., from the past, and they give us insight into the past. So some of the most picturesque spots on Earth are composed of sedimentary rocks. A lot of the American Southwest has some really pretty weathered away and eroded away sedimentary rocks. The layers can often, sedimentary rocks can occur in a number of varieties and colors, and you can get layers of different colors and get really dramatic landscapes from that. So the Colorado Plateau of the southwestern US is a particularly outstanding display of sedimentary rocks and what you get from their erosion. Because that whole plateau was flat and it built up over a long time and then got upthrust. And so various forces then dug through it. So you got things like the Grand Canyon. So types of sedimentary rocks. There's two main types. There's detrital sedimentary rocks, which are made of solid particles from weathering. Rock breaks down, the little pieces get carried somewhere else, and they get cemented together to form a new rock. These are classified by the size of their particles. So these are things, if they have large particles, like gravel-sized particles, they're either, if they're round, they're called conglomerates, or if they're angular, they're called breccia. If they're sand-sized particles, it's called sandstone. And then if they're like mud or clay or like silt-sized particles, that's shale. So these are detrital, and sometimes you also get called mudstone. Siltstone or mudstone or shale are terms that are used. So if they're gravel-sized, so the particles are named based on their size. So if they're, these are all considered gravel, but if it's over 256 millimeters, it's a boulder. That's 25.6 centimeters. That's a little bit less than a foot. If it's 64 to 256 millimeters, it's a cobble. That's a few inches across, because 64 is a little over a little over 2 inches. About 2.5. From 4 to 64 is a pebble. And then 2 to 64 millimeters across is a granule. They're pretty much arbitrary names, but they're just categorized based on their size. If they form a rock, if the particles are round and have been carried, these things get made round by being carried along in water. This is conglomerate. So one of the ways we knew there had been water on Mars was we found conglomerate on Mars. And those rounded pebbles in it only could have formed in a stream. And then if the particles are angular, it is breccia. So you can see here, these are little round pebbles. And here they're much angular blocks. That's breccia. Then if we're dealing with sand, you get sandstone or arkose, which is from a 1/16 of a millimeter up to 2 millimeters. And then below 1/16 of a millimeter, so 100 from 1/256 to 16 millimeters is silt, and below 1/256 is clay. And you get shale or mudstone, that's mud, and siltstone are what form. And you can see these are much finer. So here, we have from fine grain, it's like a shale, to coarse, this is like a sandstone, and then this is a breccia, I believe, the very coarse. So here's a short video about the formation of clastic sedimentary rocks. We'll see if the problem I was having.
Clastic rocks are the most common type of sedimentary rocks found on Earth's surface.
This mini video describes how these rocks are formed.
Check out this related video for a discussion of the classification for all types of sedimentary rocks.
There are 3 steps in the formation of clastic sedimentary rocks. Clastic sediments are composed of fragments of rock. In fact, a clast is a technical word geologists use to describe a rock fragment. These fragments weathered from pre-existing rocks to form sediment of various sizes. This sediment is then transported away from its source area, and finally it is deposited and converted to form a new rock through lithification. So let's take a closer look at these processes, starting with the breakdown of rocks by weathering.
Rocks break down on Earth's surface to form sediment. The resulting rock and mineral fragments may then be further physically or chemically weathered to form even smaller grains or other minerals.
For example, individual feldspar minerals are weathered out of this igneous rock. Notice the grains of sediment at the base of the outcrop.
Sediment like this is then eroded by transportation agents such as streams, winds, and glaciers.
This river in Alaska is carrying a high sediment load as reflected by the muddy color of the water and the sand and gravel bars in the stream channel.
Much of western Oklahoma and northern Texas lost their topsoil to winds during the Dust Bowl era of the 1930s, and we see similar dust storms today in drought-stricken western states.
Elsewhere, dust and sediment from the Sahara Desert may be transported across the Atlantic Ocean to Central and North America.
Finally, sediment of all sizes is transported by glaciers. For example, the dark surface of the Reed Glacier in Alaska reflects that sediment is exposed as ice melts. If we look closely at the glacier, we can see layers of sediment encased in the ice.
The last stage in the formation of clastic sedimentary rocks occurs after the transporting agent loses energy and the sediment is deposited.
As more and more sediment builds up, the material at the base of the pile is compacted. Compaction squeezes out spaces between grains and pushes the grains closer together. Finally, chemicals precipitate out of water to cement the grains together and form a rock.
These processes result in sedimentary rocks like shale, sandstone, and conglomerate.
So as we finish up, how confident are you that you can meet the learning objective for this lesson?
Now, there are also chemical, biological, and organic sedimentary rocks. The other way you can get minerals removed is you can have chemical weathering, where various minerals get dissolved and carried away by water, usually. So various ions get carried in solution to lakes and seas, and then some process causes them to stop being in the water and start being solid. This can be just evaporation. There is evaporates. So there are dry lake beds out there that have layers of various minerals that precipitated out as less and less water was in the lake bed. So if you've heard of the Bonneville Salt Flats, the Bonneville Salt Flats used to be a lake, and it evaporated, and all the minerals in the water in the lake, or it used to be like a sea, inner sea, and all the minerals collected and built up in layers. That's evaporates. You can have things, so and then you can also have in caves, limestone dissolves easily. The calcite and limestone dissolves. So you can have that come out. But it can also be brought out by living things. So a number of living things use various minerals to make hard parts of their bodies. And so they can extract those from, say, seawater, turn them into shells or bones or whatever. And then when they die, that settles to the bottom and forms things like limestone. And these are classified by their composition, things like, and then you can have other ones as well. So things like limestone, gypsum, chert, coal, these are all various things where it's settled out. So we can split them. These are chemical, biological, and organic sedimentary rocks. These are all calcite, various types of limestone, basically. And there's basically two groups. There's limestone that isn't made of living things. It's not organic, inorganic limestone. So you can have fine to coarse crystals, which is crystalline limestone, very fine grained crystals, that's microcrystalline limestone. And targetine, which is formed in layers, and it forms from evaporation and like hot springs. And then you have, if you have visible shells and shell fragments, that's coperina, various size shells covered in calcite cement. That's fossiliferous limestone, and microsulfic shells in clay, that's chalk. So, you know, this is a biochemical rock. And then you can have quartz. So these are chert. You may have heard of flint or other things. So cherts are caused by where water dissolves silica out of certain areas in the rock, and then it concentrates in nodules, where it grows tiny, tiny crystals to form cherts. And flint is a chert. But specifically, flint is chert in Europe, basically. There's some distinctions that make that. And so you can get these chert nodules, you get these nodules of chert, it's just tiny, tiny quartz crystals. But you also get, interestingly enough, so that's flint and other nodules of chert, but if you've also heard of petrified wood, that same process can actually happen to like buried wood and create petrified wood. So petrified wood is often also chert. There's gypsum, which is an evaporate. You have a body of water with these dissolved things in it, or you've water, and then, well, you can have various reactions that form it underground, but you can also have it evaporate away. That's calcium sulfate, 2H2O. It's gypsum. We use it to make drywall. Halite, that's salt. This is fine to coarse crystalline. And then altered plant fragments, fine grain, that's coal. So if you have a swamp that builds up material over a long time, turns it into peat, and then that gets buried and compressed, that turns into coal. And basically the conditions that can make coal don't exist anymore. So all the coal from Earth is from about 300 million years ago, roughly, I remember. So here are some examples. These are the White Cliffs of Dover. These are big chalk deposits on the coast of England. So this is a video about chemical sedimentary rocks. And chemical sedimentary rocks can be, organic or inorganic. The inorganic ones are just ones where you have processes that generate them that doesn't involve living things. Organic ones involve living things. And then there's like biochemical ones, but yeah. So
Chemical sedimentary rocks are one of the three major types of sedimentary rocks. This mini video explains how they're formed.
Imagine you took a tablespoon of salt and dissolved it in this small beaker of water. Then you added the water to a pan on the stove and cranked up the heat.
As time passed, in this case about 4 minutes speeded up, the water would gradually evaporate, and the salt concentration in the remaining liquid would get progressively higher until the salt began to precipitate out of solution.
You can see the salt crystals forming here and along the edges of the pan. Eventually, when all the water is gone, the pan will be coated with the same salt that was originally dissolved in the water.
Essentially the same thing happens in nature, just not as quickly. This occurs when water in isolated seas or lakes evaporates, leaving behind dissolved minerals.
For example, ancient Lake Bonneville covered much of Utah 10,000 years ago. Most of the lake dried up, leaving the flat lake bed covered in a layer of salt.
Because these chemical sedimentary rocks form by evaporation, they're known as evaporites. As seawater evaporates, the concentration of salts changes, and the different rocks are formed.
Gypsum will precipitate first, followed by rock salt as salt concentrations increase in the shrinking water body.
Minerals are also dissolved in lesser concentrations in groundwater and freshwater lakes and rivers, and are also concentrated in hot waters associated with thermal features such as hot springs and geysers.
Precipitation in these cases occurs when there are small changes in water chemistry.
For example, water evaporates in caves to leave behind limestone deposits. Each water drop loses carbon dioxide and deposits a film of the mineral calcite, which eventually builds up to form features such as these stalactites.
Gases are also lost as warm groundwater comes to the surface and minerals precipitate to form travertine, a type of chemical limestone which forms these terraces in association with hot springs in Yellowstone National Park.
Elsewhere, silica-rich groundwater may replace limestone to form irregular chert nodules, or produce chert when it precipitates in buried trees to form petrified wood.
So to summarize, chemical sedimentary rocks are typically formed as a result of evaporation or precipitation from mineral-rich waters.
Finally, how confident are you that you can successfully meet the learning objective for this lesson?
So the process by which these rocks form is known as lithification. So by the process by which sediments are transformed into sedimentary rocks is called lithification. And there's two main steps. There's compaction, where you have loosely packed particles get compacted to form and the empty spaces are pushed out by the pressure from the overlying sediment squishes them together, squeezes out all the empty space, and then that is followed by cementation. So various minerals can basically precipitate out of groundwater, things like calcite, silica, or iron oxide, and cement glue together the various particles. So we basically do this artificially with concrete. Concrete's artificial sedimentary rock. We induce the cementation process by having chemically triggering it with cement. So many of the inherent characteristics of sedimentary rocks are used by geologists to get a better understanding of the conditions under which these were deposited. Things like rock color, grain rounding, grain sorting, bedding, the fossil content, ripple marks, mud cracks, footprints, and even raindrop prints within the rock could tell you about the rock's origin and history. So you can know what was living around then, you can know what was going on temperature-wise, things like that. So some examples, the color tells you things about the conditions under which it was formed. Gray shades are common in sedimentary rocks. These indicate the rock was deposited in shallow, well-aerated marine waters because it has some carbon remaining. And it isn't particularly oxidized, but things like iron and such are not oxidized. Yellow, brown, and red indicate the rock was deposited on land above sea level in the presence of abundant oxygen. Because things like these are all indicators of iron oxide, rust. And dark gray to black rocks contain abundant amounts of organic carbon, which means they weren't exposed to a lot of oxygen, because these accumulated and stagnant oxygen poor areas, because if they accumulate in oxygen well aerated or oxygen rich areas, that carbon would get consumed. It would be turned into carbon dioxide, basically. Or reprocessed into things. It could rot away. So also things like the grain shape. Angular grains indicate the sediments weren't transported very far. that we've carried a relatively short distance, while rounded grades indicate long transport distances and vigorous water or wind action that wore away the sharp edges. Larger grains indicate strong currents deposited with the sediments, because as the current slows down, the heavier things fall out. Smaller grains indicate that it was a very quiet environment, because smaller grains are more easily carried by flowing water. So has to still down for things to deposit. And sorting is the degree to which sediments are separated according to size. If they are well sorted, they are comprised of grains that are all about the same size. These have been transported a long distance and over long periods of time, because the sorting process involves being carried through streams generally. Poorly sorted sediments are comprised of grains of vastly different sizes. These indicate usually a short transportation distance or time, or they might have been carried by a glacier. Glaciers don't sort. Now, strata or beds, sedimentary rocks get laid down in layers. These are accumulated layers of sediment over time, and they record past environments, and they let you look back in history by looking at older layers of the sediment. So as you dig down, you go further back in history. And fossils, or traces or remains of prehistoric life, these are the most important inclusions. They're the primary tool used to date rock layers as time indicators. They help determine past environments. And they're used for matching rocks from different places. Because, if you're finding the same species in different places, that probably is around the same time throughout history. They hadn't gone extinct yet. They give you a range of time periods where the rock could exist. So here are some features. Here are some examples of things from the environment. You can have ripple marks. You can have this things. You can have fossils as well that are clues to the past. Here's an example of bedding in sandstone. You can see the various layers. Some are thicker than others. That tells you things about how much sediment was being deposited. So that was sedimentary rocks. So sedimentary rocks are rocks formed from the pieces or the broken down bits of existing rocks. Metamorphic rocks are rocks that are exposed to heat or pressure and are transformed by that. So metamorphic rocks formed from pre-existing igneous sedimentary or metamorphic rocks. This takes place due to temperatures and pressures that are unlike those in which it formed. Because if the temperatures and pressures were like where it formed, you'd just have the same rock. So they get carried somewhere, something changes. And this leads to changes in mineralogy. So you could have minerals change. Some minerals can break down and recombine into other minerals. New minerals can form. Changes in texture. You could have continued crystal growth or crystal regrowth kind of thing. So that can change the texture. And changes in chemical composition. You can gain or lose various chemicals through exposure to active liquids. Metamorphism often progresses incrementally. So sometimes you can have a series of changes that occur, where you have somewhat metamorphosed, more metamorphosed, even more metamorphosed, and then you could have the most metamorphosed, and then finally, even more heat and pressure, it would melt. So the degree of metamorphism can be exhibited by the rock texture and the mineralogy. If it's a low-grade metamorphism, there's only slight changes, like shale becomes slate. If you look at shale and you look at slate, they're that different. Slate is more useful for certain things, but yeah, they aren't hugely different. But you can have high-grade processes like the obliteration of original features, where shale can become gneiss. And gneiss and shale don't look anything alike. Shale is a dark rock that has tiny, very fine-grained sedimentary rock. It's usually dark. Gneiss has distinctive colored layers. It's got different minerals in it. So this is, here's shale, loosely packed clay minerals, to tightly packed chlorite and mica minerals. So shale to slate. That's a low grade, relatively low temperatures and pressures. But you can have something like granite, or even shale can turn into a gneiss under high grade metamorphism with strong compressional forces, high temperatures and pressures. You have randomly oriented minerals, and then you have these bands and folding, deformed layers of various segregated minerals. That's something that happens with high grade metamorphism. So the agents of metamorphism. The three main things that cause metamorphism are heat, pressure, stress. So you can have confining pressure from burial and differential stress, where you have more pressure in one direction than the other. That occurs during mountain building. And then lastly, chemically active fluids. That's usually water, mainly water and other volatiles. These can promote recrystallization by allowing ions to move around, because you can dissolve ions from one mineral and redeposit them on another bit. So the parent rock is the original rock from before metamorphism takes place. And in addition to heat, pressure, and fluid activity, the composition of the parent rock helps determine what metamorphic rock forms. It's your starting material. So if you start with, you can't get totally drastically different material than the parent rock you started with. So the overall process of metamorphism can change both the texture, crystal size, and the mineral composition of the parent rock, but the chemicals that make up those minerals had to be there. So it's not like you're getting, so if you have, or the metamorphism can only change one of these characteristics. So one example is that where only one thing changes. If you have limestone that's exposed to high heat, it recrystallizes, the crystal structure changes, but the mineral composition doesn't. It stays calcite, and it turns from limestone to marble. So in general, if the parent rock contains only one mineral, the metamorphic rock will also be comprised of that same mineral. If it's all one substance, you're likely to still have the same substance afterwards. Usually when you get new minerals forming or recrystallization, that's because it can sort of shuffle materials in between them. This isn't always the case, but you can have this. Like, for example, sometimes you can have, say, aluminum coming out of rocks to form corundums, like sapphires or rubies. For example, limestone as a parent rock will metamorphose into marble. Both of these are made of calcite, calcium carbonate. The structure of it is changed, but not its chemical composition. So this is limestone, and this is marble. Another example of this is the change from sandstone to quartzite, where again, they're both only one mineral. They're both just quartz, but quartzite is much more tightly bound together because everything is recrystallized. So when sufficient heat and pressure are applied to sandstones, the grains fuse together to form the very resistant rock quartzite. So quartzite's a lot tougher than sandstone because it's been recrystallized and everything is bound together much better. And if the parent rock is composed of several minerals, the process of metamorphism can create a new suite of different minerals. And these new minerals are formed in response to the escalated heat and pressure conditions. So shale is a very fine-grained mixture of several minerals, quartz, clay, mica, chlorite. And depending on the degree of metamorphism, shale will be progressively changed into slate, schist, or gneiss. So you can go from shale to slate, to phyllite, to schist, to gneiss. as you increase temperature and pressure. And if you increase temperature and pressure beyond this, it would melt. So the main forces involved are heat and confining pressure and differential stress. So confining pressure is equal pressure from all directions, just you're buried underground, so you're being squeezed. But often you'll have differential stress, where you have more force in one direction than another, especially during like mountain building processes. And this can cause one direction to be squeezed more than the others, and you can get grains rotating and getting flattened to a line in that direction. So this is a short video about confining pressure and differential stress.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the difference between confining pressure and differential stress, and describe the sorts of metamorphic rocks that form in both situations. So here's an image from your text. You'll see here that we have an illustration of confining pressure. The idea here is that just loading by sedimentary layers is compressing the rocks at the base of the stack. So higher up in the stack there's less confining pressure, and at the bottom of the stack there's more confining pressure. But this pressure is the same kind of pressure that you feel if you dive to the bottom of the swimming pool, or if you drive up over a high mountain pass and you feel your ears pop. What's going on there is that you are experiencing a change in confining pressure, but the pressure is the same in every direction. So it's the same magnitude in every direction. That's in contrast to differential stress. With differential stress, the pressure is greater in one direction than it is in other directions. This is the sort of thing we would expect in geology at convergent plate margins, where two plates are crunching into one another and shoving up a mountain range. The tectonic stresses are greater than, say, the vertical stresses due to gravity. So mountains end up rising, and the rocks end up deforming. So here's an example of what can happen under differential stress. This rock here used to be a conglomerate, a poorly sorted sedimentary rock, but then it ended up being deformed and metamorphosed, and it became a metaconglomerate. Because the grains are oriented vertically here, we can deduce that the greatest differential pressure was oriented from side to side. With that in mind, take a look at this example. Here's another metaconglomerate. Which way would the maximum differential pressure have been oriented to produce this rock? Hopefully your answer would be something like this. And the reason we know that is that the grains basically elongate in a perpendicular direction to that maximum stress. So the basic idea here is something like this. Before metamorphism, under differential stress, we have grains at a random orientation. After metamorphism, those grains are dominantly aligned in a new direction, and the overall shape of the rock has changed. There's two different ways to accomplish this. One way is through slip within a mineral crystal. So the bonds that hold together the atoms inside a mineral crystal can actually slip relative to their neighbors. So one block of atoms can end up sliding relative to its neighbors, and that happening many, many times throughout the crystal, essentially lots of little tiny, almost like a fault, will end up deforming the crystal in a new shape. So you basically go from an original spherical shape to a more elongated shape afterwards. Another way to do it is through pressure solution, and this is something that happens with certain minerals that are susceptible to going into solution when they're put under lots of pressure. So if you squeeze them top to bottom, some of the material is going to end up dissolving, and then it'll flow to a new location where there's low pressure, and it will precipitate there. So the mineral crystal will actually lose material from one spot and regrow it somewhere else. And again, the effect is to go from an original, more equant grain to something that's more elongated afterwards. Here's an example of a metamorphic rock. Let's see if you can figure out whether it formed under confining pressure or differential stress. It was a conglomerate, and then that conglomerate got metamorphosed into a metaconglomerate. So what's the deal here? Confining pressure or differential stress, and what's your evidence? Hopefully you notice that the grains here don't seem to have any sort of common orientation in the metaconglomerate, and so therefore if they're not elongated, then that means that they formed under confining pressure only. Here's a different example. This is a gneiss. This gneiss has long stringers of different colored minerals running through it. So confining pressure or differential stress? Good. I assume you said differential stress, and in this case the differential stress probably would have been coming from the direction marked B on this diagram. Thanks very much for your attention. This has been another Smart Figure.
So that's known as, that elongating or flattening is known as foliation. That's the flat arrangement of mineral grains or structures, where minerals end up perpendicular to the compressional force. This is common in slate, phyllite, schist, and gneiss. But some metamorphic rocks have a non-foliated texture. They contain equidimensional crystals. You have a coarse grain, it looks like a coarse grained igneous rock. These are things like quartzite or marble. So this is a video about the way that the rotation of plating and elongated mineral grains to produce a foliated texture. So here we have before metamorphism, we have confining pressure.
This animation illustrates how differential stress can cause the rearrangement of mineral grains during metamorphism. This process results in the mineral grains becoming aligned roughly perpendicular to the direction of maximum stress, creating one kind of foliation.
Oh, there was that animation of that. And here are some common metamorphic rocks. We have slate, the image of the texture, it's fine grained. It's got tiny chlorite mica flakes and breaks and flat slabs called slaty cleavage, and it has smooth, dull surfaces. It forms from shale, mudstone, or siltstone. Phyllite is fine grained, glossy sheen, breaks along wavy surfaces. This also forms from shale, mudstone, or siltstone. It's just more metamorphosed than the slate. Schist, even more metamorphosed than the phyllite. Schist, which is medium to coarse grained. It is a scaly foliation, as mica is dominant. Again, it can form from shale, mudstone, or siltstone, or from slate or phyllite. Gneiss is coarse grained. It has a composite. It has banding due to the segregation of light and dark colored minerals. This has forms from shale, granite, or volcanic rocks. Here we have marble. It's medium to coarse grained. It is relatively soft. It has interlocking calcite or dolomite grains. It forms from limestone or dolostone. And then quartzite is medium to coarse grained. It has very hard, massive fused quartz grains. That's a quartz, forms from quartz sandstone. So when we look at metal resources from rocks and minerals, there are various metallic mineral resources, things like gold, silver, copper, mercury, lead, etc. These are generally produced by igneous and metamorphic processes. These various metallic ions get carried out in igneous or from deep within the earth via igneous and metamorphic processes to get deposited. Most important ore deposits are generated from hydrothermal or hot water solutions of these. You get pegmatites that form in fluid-rich environment, having usually large crystals. You could have vein deposits and fractures or bedding planes, and disseminated deposits that are distributed throughout the rock. But you usually are carried up by water from deep or below. So here, if you have an igneous body and associated pegmatites and hydrothermal mineral deposits, so you have the magma chamber, then around the edges you get pegmatite deposits, and then hydrothermal disseminated deposits and hydrothermal vein deposits, where that water flows through cracks and deposits. So this is a high-grade ore deposit, gold ore deposit in a quartz vein. You have quartz with gold running through it. Now, non-metallic mineral resources are interested in using the mineral's non-metallic elements and its various physical or chemical properties. There's two broad groups. Things like building materials, like limestone or gypsum, get used for building materials. Limestone is an important ingredient in making cement for concrete. And gypsum is what we make drywall out of and other things. And industrial materials, things like fluorite, corundum, and sylvite are all used in various industrial processes. So fluorite is used as a flux for steel making and other processes with that. Corundum is used as a abrasive. And sylvite, I'm not sure off the top of my head what sylvite is. Oh, sylvite's a sulfur ore. There's a lot of stuff we do with sulfur chemistry and sulfur. So, apatite is used for phosphorus fertilizers. It comes from sedimentary deposits. Asbestos has incombustible fibers. It comes from metamorphic deposits. But also is good at other things like ruining your lungs. Calcite is used as an aggregate in steel making and soil conditioning and chemicals and cement as building stone. This comes from sedimentary deposits. Clay minerals are used in ceramics in China. This is a residual product of weathering. Corundum is used for gemstones or abrasives. It comes from metamorphic deposits. Diamonds are used for gemstones or abrasives. They come from kimberlite pipes or placers. Fluorite is used in steel making, aluminum refining, glass, and various other chemicals. These come from hydrothermal deposits. Garnet is used as abrasives or gemstones. This comes from metamorphic rocks. Graphite is used in pencil lead as a lubricant as a refractory material. This comes from metamorphic rocks. Gypsum is used in plaster of Paris, so plaster, drywall. It comes from sedimentary deposits, evaporates. Halite is used as table salt to various chemical processes like ice control, sedimentary deposits. Muscovite is used as insulators in electrical applications because you have those nice thin sheets. This comes from igneous intrusions and pegmatites. Quartz is the primary ingredient in glass. This comes from sedimentary deposits from sandstone. Sulfur is used in various chemicals and fertilizer manufacture. This comes from sedimentary deposits and hydrothermal deposits. Sylvite is a potassium ore. It's used in potassium fertilizers, so sedimentary deposits, various evaporites. And talc is used in talcum powder, used in paints, powder used in paints, cosmetics, etc. And that comes from metamorphic rocks. Also, there are energy resources. Coal burns the energy that was stored by plants millions of years ago. Problem with coal causes surface scarring and air pollution and global warming. Oil and natural gas generate more than 60% of US consumed energy. That might be a bit out of date. These are the remains of marine plants and animals. The source rock is where the oil and natural gas originate. And oil trap is a geologic environment allowing oil and gas to accumulate. Because if they're actually exposed, that could be a problem. You have some reservoir rock, which is porous and permeable. This will yield oil and gas in significant quantities. And then you have a cap rock, which is impermeable, which will keep the oil and gas from escaping to the surface. Because if they did escape to the surface, they would just decompose or fly out. So some common traps are anticlines, faults, salt domes, or stratigraphic. And we don't have time for this. So I think I'll go over the energy resources stuff again next time, and then we'll start chapter 4.